Here we are trying to understand how to calculate flux. So let's have a coordinate system drawn for us. So that's our x direction for reference, and that's our y direction. So this is x, and that's y. In this, with these directions given to us, the electric field is there is a uniform electric field which is which has a direction and magnitude. But to get the direction sense, there is one unit in the x direction, and there are two units in the y direction. Right? So that's roughly how we can see what's the direction of the electric field. So that's your vector E that we have. But electric field is a field and not just one vector. So we have a uniform electric field, which means we will have something like this. Okay, everywhere we have electric field, and I'm keeping it equidistant, trying to keep it equidistant as much as I can. And that represents uniform electric field lines. So let's show the arrows here. So that's, and they should be imagined or visualized as a flow. So there is a, think of a liquid flowing, and if you keep something in it, a mechanical object tries to get in the flow here. This is an electric field, and this affects affects any charge that's in its flow. So this is a flow of electric field lines. This particular line being the particular vector at origin, and any charge in this experiences a force or a push. If it was a positive charge, it gets pushed in the direction of the electric field, and if it is a negative charge, it gets pushed in the opposite direction. So that's the electric field idea. And now we would like to think of the flux of the electric field, how much electric field is going through a particular region, and that's described, that's quantified by a quantity called electric flux, which is defined to be the integral, a surface integral. So that's two integrals at this point. So two integrals is represented by an area vector. Area is always a vector and dotted with the electric field. But it's a uniform electric field, so it doesn't matter where you are in this integration regime or integration domain. The electric field is a constant, so this is over the plate, right? Over so through a rectangular plane, so we have a small plate on which you're actually integrating, whose length and width is given to us. Since the electric field is uniform, it can come out of this integral, and we can write only if it is uniform. This comes out, and I put it on the front side, and this whole integral is just having the area now. Area again being a vector, and which I will describe very soon in this picture. At this stage, this is only the area that's involved in the integral. So integral over a differential area with nothing else in it will give us the total area. So this will be equal electric field dotted with the total area. So A being the vector representing the plate under consideration. So area of the plate. Vector, let me say this is vector area of the plate. We are told that the rectangular plane we have, or rectangular plate we are talking about, is 0.4 into 0.2 meters square uh, in area, and it is parallel to the YZ plane. So we have X direction here, Y direction in the vertical direction. Z will be coming out of the page. Remember, Z has to be equal to X crossed with Y. So the right hand rule gives us that Z has to be coming out of the page. So that's the direction of uh, of Z. So when we say it is the YZ plane, YZ is the plane with the Y axis and coming out of the plane. So YZ plane, what's a perpendicular direction to that? It has two directions. It can be either in the plus X direction or in the negative X direction. Let's choose one of them. So, and let's say it is in the positive X direction. So that's your area vector A. And let me refer this to be the electric field pointing. And this could be the plate itself. Let's represent it as a cross section we are showing. This could be the plate, right? So it's a finite plate. It has 0.4 meter by 0.20 long. It doesn't matter in what orientation it is in the YZ plane as far as the electric field is going through. So if you see this as a plane now, you see that there is electric field going in this direction here, where it's crossing that plane. And we would like to calculate all this electric field passing through this, only this much. That's your plane, and how much electric field is causing. So the flux is a quantification of that quantity. This is a dot product. So electric field is equal to 1.0 I hat plus 2.0 J hat and to 10 raised to 3 newtons per coulomb. So it's your electric field. And the area vector now we showed here is that it's pointing in the x direction, and the area itself is magnitude of the area. So let me say magnitude of the area is equal to 0.40 meters times 0.20 meters. So that's 4 into 2, 8. That's two sig digits. So 8 into 10 raised to minus 2 meters square. That's a magnitude. So we have area, I will write it as 8.0 into 10 raised to minus 2. So let me write that as I hat plus 0 j hat. There is no direction for the vector area in the j hat direction. It's purely in the x hat direction. Area, again, remember, is always perpendicular to the plane containing the area. The plane is in the yz direction, so the vector corresponding to that area will be perpendicular to that, which is in this case in the x direction. It's also the power here, so that's 10 raised to minus 2 meters square. So the flux, which is the dot product of the two quantities, is now easy to see. We multiply the I hats together plus the j hats. J hats multiplied gives you 0. So that's 1.0 into 8.0. And then the powers also is 10 raised to 3, 10 raised to minus 2, and Newton meter square over Coulomb. That's our units. The flux of the electric field does not have a standardized or a name for a unit, so we just have to write it in this form. So that's 8.0 into 10 raised to 1 Earth's remaining, so it's 80 with two sig digits, Newton meter square over Coulomb. That hopefully describes an example where we calculate the electric flux, illustrates how electric flux is an important quantity. Let me stop the recording here for this.